Hello, everyone. Today, I'm going to present our research project that is called AnyOpt. So this work focuses on predicting the Anycast catchment and also optimize the IP Anycast performance. And this is a joint work that collaborates with many companies and also institutions, which is listed on these slides. So first, let me introduce what is IP Anycast. So IP Anycast is a routing paradigm that allows you to announce the same IP prefix from multiple different locations. Take this graph as an example. There are 3 Anycast sites. So each site can announce the same IP prefix to the internet. So after the BGP got converged, that means the internet BGP got converged, different clients will get its catchment area. So each different client will just send its request to the corresponding catchment sites. So for example, in this graph, after the BGP announcement got converged, the whole internet got split into 3 different catchment areas. So the host in different catchment areas will only send a request to its corresponding Anycast sites. And because of this specific feature, Anycast is adopted by many geographical distributed service providers. So for example, some DNS and also CDN and also DDoS mitigation system, they're all using, most of them are using IP Anycast to provide the service to improve their performance and also resilience. So what do we expect for the IP Anycast network? So in the ideal case, for the round trip time reduction, we expect every client will get access to the nearest Anycast sites. So that means it will choose the optimal size regarding considering just the round trip time. So in this graph, we show an example of Anycast network, which composed with 3 different Anycast sites. So 1 in Chicago, 1 in London, and 1 in Singapore. We also have a bunch of clients that want to get access to this Anycast service. So in terms of the performance, each client should select the size which provides the minimal round trip time. So that's how the optimal catchment should be like. So each client will choose the optimal catchment site, which is the result is stand by different colors. So the red dot stands for the clients can get optimal performance from the Chicago site. So in this case, the average latency will be only 62 milliseconds if each client can select the site with just minimal round trip time. But we also deploy the same identical configuration and announce our experimental prefix to those 3 Anycast sites, and we got the real catchment area like this. So that means the majority of the clients actually was covered by Singapore site's catchment area. So that will result in a very hard problem. So that's very bad performance. So in this case, we also measure the performance of all clients around the world. So that gave us an average round trip time for all clients. That's 133 milliseconds. That's almost twice as the ideal case. So this also tells us in the real Anycast network, the clients does not necessarily select the optimal Anycast sites. That means clients always reach far away sites. So there have been several previous literatures also confirmed this scenario. So like 3 years ago at the SIGCOMM, Lee et al. Claimed that around 1/3 of the DNS queries actually suffer from serious Anycast inflation. So that's the thing we just discussed. That's clients cannot always select the most efficient Anycast sites. And also Calden et al. And Koch et al. Also confirmed that with the trace data from Microsoft Anycast Cloud. So they say that only 20% to 35% of users experience serious Anycast inflation. And there is also another work tell us how to measure the Anycast catchment efficiently. So here comes the challenge on how to improve the performance of Anycast performance. So at first, a service provider needs to select a subset of the Anycast sites to announce the Anycast service. But the problem is the BGP protocol usually determines a site's catchment. the problem is BGP is usually performance agnostic. And that show us that increasing the number of sites does not always reduce latency. And this is also confirmed by several previous literatures. So here comes the question. In order to optimize the performance of Anycast Cloud, we need to answer this question: how to choose a subsite from potential Anycast sites to minimize the client's latency. And in order to do that, we first need to solve the problem of how to estimate in latency, and that requires us to predict the catchment for the Anycast networks. So we will have a strawman approach that will solve this problem. So first step, we'll experiment all possible subsites of all available Anycast sites, and then for each subsite, we'll deploy this configuration and also measure each site's catchment and also average client latency. And in the end, we can just choose the subsite with minimal average latency. But this methodology has a very serious problem, that is the scalability. So the number of experiments we need to do in this strawman approach is exponential in the number of sites. So in order to solve that problem, we propose AnyOpt. So AnyOpt is a method to do the Anycast network optimization, follow a three-stage method. So that is measure, model, and optimize. So in the first step, we'll measure a client's preference order between each pair of Anycast sites. And based on this method, we will consolidate those information into a linear order among all available Anycast sites for each client. And we can also measure the round trip time from different clients to different Anycast sites in a similar way. And then we can model a client's route selection behavior as a linear preference order. And in the end, with both of those information I have just mentioned, so one is the total order among all available sites, and the other one is the round trip time from different clients to the Anycast sites. With those information, we can just solve this problem in an optimization way offline, so that we can choose the optimal subsite that can minimize the round trip time. So first, let me introduce what is the linear order we used in this case. So at the beginning of this project, we have a much smaller like Anycast network, so that we can try every possible subsites of the potential Anycast sites. So in that experiment, we found that actually a majority of the clients select their Anycast sites according to a linear order. So take this graph as example for one specific client here. It will have 3 Anycast sites, which will potentially announce the prefix. And we tried all possible combinations of those sites, and we found out actually the client selects the optimal catchment site following that linear order. So that means the clients will prefer the Anycast site A the most, then follow the B, and it does dislike the Anycast site C the most. So with this total order, we can it will enable us to have the capability to predict the catchment site for any possible combination of those sites. So for example, if we only enable Anycast site A and Anycast site C here, the Anycast A will be selected in the end. And if we only enable Anycast site B and Anycast site C, the Anycast site B will be selected. And if we enable all Anycast sites, the most favorable one, so that's the Anycast site A, will be selected. So there have several related work trying to control the catchment area proactively or doing some inference work to predict the catchment. So the first one is Azubi et al. They propose to use MPLS-based catchment control method to manually assign the ingress point to Anycast sites which are assigned into the single same AS manually. And the other work is Suspense et al. They propose a method to use public BGP feeds and also the AS relationship topology to infer the catchment area for one specific AS. But our work here use the measurement work conducted by ourselves to build the whole total order for each client, and based on that total order, we can make the prediction and also minimize the Anycast round trip time latency. So here, let me introduce how to get the total order of the clients. So we get the total order based on the pairwise site comparison result. So for the pairwise preference discovery, we'll announce the same prefix to 2 of the available sites. And after the BGP got converted for the internet, the whole internet will be divided into 2 parts. So each part will belong to just one site's catchment. So in this graph, we can see client X belong to Anycast site A's catchment, and the other 2 belong to the other one. And then we will send out SMP packet to all clients at the same time. And based on the catchment area, the client will only reply the packet through one specific tunnel. So based on this, we can see the request to client X will only return through the tunnel between Anycast site A and our orchestrator there. And the other 2 will reply the SMP packet in another way. So based on that, we will know for client X, the pairwise comparison result is that the client X will prefer Anycast site A more than B. But for the other 2, they will have another kind of preference order. So that is, they prefer Anycast site B other than A. So this will allow us to reduce the number of experiments to just quadratic in the number of Anycast sites rather than the exponential. Use that method, we will get the total order of all clients, but we still need to get the round trip time from different clients to the Anycast sites to make the prediction. So in order to get the round trip time from different clients to the Anycast sites, we will announce the Anycast prefix to one single Anycast site. So that means we'll announce the prefix in a unicast way. And after the internet got converged, all the clients will belong to the single site's catchment area. And after that, we'll send out SMP packet to all clients. And the client's reply will return back through the same tunnel. Then we can get the round trip time by subtracting the total travel time with the tunnel travel time. So in order to evaluate how many clients actually can have the total order, we deployed a moderate Anycast network to evaluate this. So we selected 15 sites around the globe, considering both traffic concentration and also geographical distribution. And we also have an orchestrator server that connects to all those 15 different Anycast sites. And they build GRE tunnel with those Anycast sites and send out the BGP announcements and also SMP packet to all those sites in order to measure the linear order and also round trip time. So besides that, we also selected more than 15,300 different routers IP. And all those routers IPs covers more than 12,000 different /24 network prefixes. And all those IPs cover more than 5,300 different ASs. So with this large scale, we can get, infrastructure, we can get all the linear order for all 15 Anycast sites for each client, also the round trip time. So those 2 parts of information will serve as the inputs for the following optimization problem. So it turns out that this optimization problem is actually exactly the same simple facility location problem with client's preference order, which is proposed around 35 years ago. But this problem is proved to be NP hard and do not have consistent polynomial time approximation solution. But luckily, for this moderate scale infrastructure, like 15 Anycast sites, we can just solve this problem like offline. So in order to justify the existence of the linear order, we also work out several different scenarios that will guarantee each client will have the linear order. So there are 2 scenarios that will allow the clients to have a consistent linear order among available Anycast sites. So the first scenario is the route selection strictly based on the preference order among all available neighbors. And the second scenario is we will only announce our prefix from tier 1 transit provider, and the following route selection strictly based on AS path and neighbor ID. So under those two scenarios, the route selection is consistent with wide-free BGP routing model, but they will still guarantee there will be a total linear order. But we also found out that there are several counter cases a linear order may not exist for all value-free BGP routing policies. So in order to get the most clients that have a linear order, we have resolved a few different problems. So the first one is the BGP implementation of the tie breaking with arrival time. So on the left side, it is the RFC file to describe how the route selection or tie breaking is done. In the BGP specification, it will follow a sequence of those all factors. But on the right side, there are the cutting edge or state of art implementation of the BGP BGP tie breaking. So we have saw that there are one more additional factors here. So that is the route's arrival time. So that means if all the above factors are all the same, the routers there will just based on the arrival time to select the optimal path. So in order to solve this problem, we just announced the prefix from two different sites in both orders. So this have a huge influence on the clients who can have a total linear order. So the right line here shows the portion of clients which will preserve a consistent linear order in the end for 15 sites if we announce them like to both of the sites simultaneously. And the blue line shows if we use an ordered linear order, ordered announcement order, what will be the portion of client that will keep that. We found out that only 15% of clients will have a total linear order if we do not consider the announcement order. But if we use ordered announcement, nearly 90% of all clients will have the total linear order, which will allow us to do a more precise round-trip time estimation. So the second problem is the scalability. So the number of experiments is quadratic in the terms of sites. That's the best we can do with the current method, but it's still a lot. So for example, if we use the 15 sites, it will take like 210 different BGP experiments to finish that. So that's also a huge number. So in order to resolve that problem, we use a two-level method. So in the first level, we just resolve the pairwise comparison among those tier 1 transit providers. So in our 15 different Anycast sites, we have 6 different tier 1 transit providers. So that will cost us like 13 rounds of different BGP experiments. And in the second level, we'll figure out how the intro AS level, but different sites preference order. So that will bring us additional 13 different BGP experiments. So in total, it will cost just 43 BGP experiments compared with like 200, like several hundreds in the previous round. So with all those like total order we have just discovered, it will allow us to do a precise round trip estimation for those 15 different clients. So in this graph, we showed how the absolute estimation error would be like. So in this experiment, we deploy 38 different random BGP configurations. So that means different subsites of the Anycast sites. And we deploy them and measure the actual round trip time. And we compare it with the predicted round trip time. Then we see that nearly 90% of all the random configuration will have an absolute estimation error less than 8 milliseconds. We also compare the performance with optimal configuration we got from the offline optimization process. So AnyOpt is the optimal configuration we got from the offline explicit enumeration. It gave us an answer with just 12 sites. And we also select 12 sites greatly based on the unicast round trip time. So it will improve the median round trip time by 38 milliseconds. And we also compare with the configuration, which includes all available Anycast sites. And compare with that, it will reduce the median round trip time by 14 milliseconds. So transit provider is just one part. We also have a large volume of peering links. So here we also measure the peering links coverage. So from the CDF, we can see around 80% of all peering links just cover 2.5% of all customers. And the different peering link will bring different impact to the overall performance. So from this graph, we add one single peering link to the AnyOpt configuration, and it will give us different influence on the average round trip time. So from this graph, we can see the impact is not uniformly. So several configurations can even like bring worse influence on the average round trip time. And we also compare with other several peering configurations. So the purple lines here shows the AnyOpt configuration plus the benefit peers. So that means the peering links can guarantee to improve the average round trip time. And we also include all peering links. So from here, we can see if we bring on all peering links, it can actually improve the performance by 7 milliseconds. So for the contribution of this project, so in this project, we proposed the linear order assumption and justified this assumption with empirical evidence and also theoretic justification. And we also built up AnyOpt, which is a system to predict the Anycast catchment and also optimize the Anycast configuration. And we also provide the evaluation with a moderate Anycast network and a large-scale client sites. But there are also several other future works for this project. So first, it's very hard to adapt this AnyOpt to larger Anycast network. For example, Akamai DNS have hundreds of sites around the world, but pairwise or just two-level method can consume too much time to finish this. And in this project, we only consider the round trip time as objective, but sometimes for Anycast services, robustness and also load balance can be also very important for the SLA. And also for the combinatorial problem for the peering links, we still cannot achieve accurate prediction for that. So that's all for my talk here. I'm very happy to take any questions.
Thank you, Shane.
Yeah.
As you all can see, Shane's advisors are joining us now. Bruce and Zowie from Boston and Durham, North Carolina.
Yeah.
We have one question from the audience. Go ahead. Mike?
Hello, there we go. Robert Story from USC ISI. It would probably explode your number of experiments, but did you look at doing any traffic engineering with any of the announcements, like prepending or communities to restrict advertisements?
Yeah, no, that's a very good question. So the community number and also traffic engineering techniques can influence this result, but that's the parts usually lies along the line, so which we could not control. So because in this project, we aim to proactively optimize the performance without cooperation with any other parts. So that should be the next step we should look into. Thanks.
We have one online question here from So how many BGP experience will trigger BGP route dampening, and how do you resolve that?
Yeah, that's also a very good question. So because frequent BGP change or updates will trigger the route damping, BGP route damping, which will influence the result. So as in my previous example for the 15 sites, it will take 210 rounds to finish all the experiments. So if we do not insert like spacing into them, actually they will actually trigger this phenomenon. So in order to resolve this problem, we wait for 1 hour to like the whole BGP to converge, and after that we'll reset that prefix. That means clean, withdraw the prefix from the internet and let the whole BGP system cool down. And in the next round, we'll do another new experiments.
Excellent. Any other questions from the audience or online? How about our virtual visitors? Do you have any questions or anything you'd like to add?
Nice job, Shane.
If we can get a round of applause for Shane and his advisors.
Thank you. Thank you.
Thank you, Shane.
Thank you.